In the early 20th century, a meteorologist named Alfred Wegener noticed striking similarities between the coasts of Africa and South America. These observations led him to propose a controversial new theory. Perhaps these and many other continents had once been connected in a single gigantic landmass. Wegener's theory of continental drift directly contradicted the popular opinion that Earth's continents had remained steady for millennia, and it took almost 50 years for his advocates to convince the larger scientific community. But today we know something even more exciting. Pangea was only the latest in a long lineage of supercontinents, and it won't be the last. Continental drift laid the foundation for our modern theory of plate tectonics, which states that Earth's crust is made of vast, jagged plates that shift over a layer of partially molten rock called the mantle. These plates only move at rates of around 2.5 to 10 centimeters per year, but those incremental movements shape the planet's surface. So to determine when a new supercontinent will emerge, we need to predict where these plates are headed. One approach here is to look at how they've moved in the past. Geologists can trace the position of continents over time by measuring changes in Earth's magnetic field. When molten rock cools, its magnetic minerals are frozen at a specific point in time. So by calculating the direction and intensity of a given rock's magnetic field, we can discover the latitude at which it was located at the time of cooling. But this approach has serious limitations. For one thing, a rock's magnetic field doesn't tell us the plate's longitude, and the latitude measurement could be either north or south. Worse still, this magnetic data gets erased when the rock is reheated, like during continental collisions or volcanic activity. So, geologists need to employ other methods to reconstruct the continent's positions. Dating local fossils and comparing them to the global fossil record can help identifying previously connected regions. The same is true of cracks and other deformations in the Earth's crust, which can sometimes be traced across plates. Using these tools, scientists have pieced together a relatively reliable history of plate movements, and their research revealed a pattern spanning hundreds of millions of years. What's now known as the Wilson cycle predicts how continents diverge and reassemble, and it currently predicts the next supercontinent will form 50 to 250 million years from now. We don't have much certainty on what that landmass will look like. It could be a new Pangea that emerges from the closing of the Atlantic, or it might result from the formation of a new Pan-Asian ocean. But while its shape and size remain a mystery, we do know these changes will impact much more than our national borders. In the past, colliding plates have caused major environmental upheavals. When the Rodinia supercontinent broke up circa 750 million years ago, it left large landmasses vulnerable to weathering. This newly exposed rock absorbed more carbon dioxide from rainfall, eventually removing so much atmospheric CO2 that the planet was plunged into a period called Snowball Earth. Over time, volcanic activity released enough CO2 to melt this ice, but that process took another 4 to 6 million years. Meanwhile, when the next supercontinent assembles, it's more likely to heat things up. Shifting plates and continental collisions could create and enlarge cracks in the Earth's crust, potentially releasing huge amounts of carbon and methane into the atmosphere. This influx of greenhouse gases would rapidly heat the planet, possibly triggering a mass extinction. The sheer scale of these cracks would make them almost impossible to plug, and even if we could, the resulting pressure would just create new ruptures. Fortunately, we have at least 50 million years to come up with a solution here, and we might already be onto something. In Iceland, recently conducted trials were able to store carbon in basalt, rapidly transforming these gases into stone. So it's possible a global network of pipes could redirect vented gases into basalt outcrops, mitigating some of our emissions now and protecting our supercontinental future.